Okay, get started. So there are a couple things that I want to, I know I sort of jumped the gun and went ahead to compactness already, but actually we need to go backwards. So there's a couple things that I should have covered, but I kind of skipped them. So the first, so we were talking about closure, right? So remember, we've got this thing called the closure of a set, right? E bar, and that was defined to be E union its limit points, right? And we saw that that this was a closed set containing the set, and in fact, it turns out to be the smallest closed set, containing that set. Okay. So one thing that is mentioned is that in R, if we have a subset of R, R1, so suppose we're in R1 and we have some subset and it's bounded above. Okay, well, being bounded above means that it's going to have a least upper bound, right? So as a supremum, right? And the theorem says that the supremum will always lie, it's kind of what you might expect, that the supremum will always lie in the closure of the set. Okay, so right, if you're thinking about R1 and you think about an interval 0, 1, an open interval 0, 1, right? The supremum is 1. Supremum was 1. It's not contained in the set itself, but it's contained in the closure of that set, right? Okay, and right, so so the proof goes like this. You say, well, right, so without loss of generality, assume that, let's call this, sorry, let X denote the supremum. Let X denote the supremum of E. And notice that if X is in E, we're done. Right, because we'd be done. So without loss of generality, we can assume X is not in E. Okay. Okay. So assume that X is not in E. Okay, and we want to show that we want to show that X must be a limit point, right? Right. We're trying to show that the supremum is in E union, is either in E or it's a limit point of E. Assume that it's not in E. We'll show that it has to be a limit point. Okay. Everybody okay? You guys awake? Yes. Good. Okay. We'll show that it has to be a limit point. Okay. And we'll do it by contradiction. Okay. So suppose X is not a limit point. Right. Right. So if X is not a limit point, what does that give you? That gives you that there's got to be some neighborhood, some punctured neighborhood around it that doesn't intersect E, right? So, i.e., there exists some neighborhood around X, some punctured neighborhood around X that does not intersect E, right? So there's some punctured neighborhood around X that doesn't intersect E. Nobody from E is inside here, except possibly X, but actually X is not in E, so it's the whole interval, right? It's the whole interval that doesn't intersect E, right? Okay. So you've got this whole interval that intersects E, right? And you see what the problem is, right? Because X is supposed to be the supremum of E, but we have this whole interval here, right? It's supposed to be the least upper bound of E. But we have this whole interval in which there's nothing of E, right? Which means that that this thing here, X minus R over 2, is still an upper bound of E, right? So notice that, but then x minus r over 2 is still is an upper bound of E that is smaller, that's smaller than x, right? And that's a contradiction, right? Because that's not possible, right? Because x was supposed to be the least upper bound, right? The least upper bound of E, but we found an upper bound that's smaller than x. Okay. Okay. So just a small fact, right? That whenever you have an upper bound of a set, whenever you have a least upper bound of the set, that thing is contained in the closure of the set. It might not be a limit point itself, right? You could have a set that looks like that, just a single point, right? That's not a limit point, but it's the upper bound. But it's contained in the closure. It's certainly contained in the closure. Okay. Okay, so there's that thing I wanted to cover. Second thing I wanted to mention is an idea that we're just going to introduce and then kind of throw away almost immediately. Okay, it's kind of an odd one, but it's so the idea of relative openness. Okay, so and we're going to kind of throw this idea, introduce it, and then throw it away, because we're talking about compact sets. And what we'll see is that we don't have to the things that we worry about that force us to talk about relative openness, we don't have to worry about in the case of compact sets. So let me show you what I mean by that. Okay, so let's think. Here's an example. So here's the idea. So suppose we're in R2. Okay. Suppose we're in R2 and we've got our usual metric, right? The usual, Euclidean metric. Okay. Let's call the x-axis x. Okay. So we've got R2 with the usual Euclidean metric, right? Use the Pythagorean theorem. Get the distance between these 2 points. Look at some subset. In this case, the x-axis, and think about that with the inherited metric, the metric that it inherits from the ambient space. Okay, is that still a metric space? So to be a metric space, what has to happen? You need something that's a metric, right? This has to be a metric, but it's already a metric, right? It satisfies the rules of metricity, or the rules of being a metric in the ambient space, so that it's not going to fail in the embedded space, right? If it failed there, it would have failed in the original space. Okay, so this is still a metric space. Okay, but the problem is that if we look at this thing by itself, the problem is that the notion of openness depends on the ambient, on the space that you're in. Okay, so like if I'm thinking just about this space right here with this metric, well, an interval AB is open, right? This thing right here, AB, right? A comma B, that's this set right here is an open set in X comma D, but it's not an open set in R2 comma D, right? Right? Because if I just ignore if I ignore R2 and think just about X, right? Well, then this is just a neighborhood, right? And every point is interior, right? Every point is interior. Right, but if I'm thinking about the entire space, right, then no point is interior, right? No point is interior because the balls are now two-dimensional balls, right? The neighborhoods are now two-dimensional neighborhoods, and so this is not open. So you have to talk about, you have to say, when you're talking about open sets, you have to say open relative to what space? Okay, so this gives us this definition. So you have some space x. Sorry, they use x as the large space. I probably should have called this one y, and called the big one x. Okay. Okay. So suppose you have a metric space, and you have a y sitting inside of x, which is also a metric space with the inherited metric. Okay. We say the set E contained in Y is open relative to Y if for all points in the space there exists an R such that if you look at the points in Y whose distance from P are less than R, then that's contained in E. Okay. So let me read this in English, right? What this is saying is that for every point, right, so let's use this as a picture again, right? So here's our point P. For every point in E, there's a radius so that if you look at the points in Y whose distance from Q are less than whose distance from P is less than R, right? Then that thing is contained in E. Okay, that thing is contained in E. Okay. So I think probably the way to think about it, maybe it's a little bit, I think it's a bit clearer to say, instead of saying it like this, you'd say, such that there exists a ball around P, right? There exists a ball around P such that the intersection of the ball with Y is contained in E. Right? That's the same thing, right? So there's a ball, right? This ball is in X. There's a ball in the ambient space, so that when you intersect it with Y, you know, the points, the thing that you get is still contained in E. It's exactly the same thing. But I think this is maybe easier to visualize. Okay. So that's what open relative to Y means, right? So, right. So every point has this sort of like intersected neighborhood, has an intersected neighborhood that's contained in the set, right? This thing is open relative to Y if every point in it has an intersected neighborhood that's still contained in the set. Okay. You guys okay? Everyone all right? Close your eyes for a second. Raise a finger from 1 to 5. 5 is good, 1 is bad. How are you feeling? Okay, put your fingers down. Okay, okay. Everybody is 3 or above, so that's all right. But that does mean that there are some 3s. But that's all right, 3 is okay. How happy do you want to be? I'm perfectly fine at 0, like kind of a flat, like just like that. My son comes from school often, and I say, "How was school today?" And he said, "It was normal." I'm like, good. Normal is okay. Okay, so let's go on. So relative openness, right? Right. So when you're talking about openness, you have to specify open relative to what. Okay. And I gotta come back. I'm going to erase this because I'll need some space. So the theorem that we're going to the theorem, the one theorem that we have about relative openness is pretty straightforward. What it says is that E is open relative to Y if and only if E equals G intersect Y for some G open in X. Okay, so in other words, any set that is open in the intersected down space must be the intersection of some open set in the big space with the internal space. Okay, right? Like so, right? It must be the intersection of somebody with the internal space. Is the statement clear? Right. Okay. So. What do you think about this? Does that seem reasonable? Right? If you're open relative to Y, what does that mean? That means that every one of your points is contained in an intersected open neighborhood. Right? So every one of these points, right? Going forwards. So this is pretty much straightforward. The proof of this is as you might expect, pretty straightforward, right? If you're open relative to Y, that means that every one of your points is contained in some sort of in the intersection of an open ball with the space, right? Right. So in that case, we can realize we just take all of those balls and put them together, and that's our G. Right. We take all those balls and put them together, that's our G. When you intersect it with Y, you're going to get E. Right? Right, so, right, we want to show that E equals G intersect Y for G open in X. Well, for each P in E, we know since E is open relative to Y, we know there exists some ball B sub r P that B sub r P that such that B sub r P intersect Y is contained in E. Right? Everybody in E has, since E is open relative to Y, we know that every one of these guys has a ball that when you intersect it with Y, that resulting neighborhood is contained in E. Right? That's just the definition of open relative to Y. Okay. Let me call these things R sub P, because the radius does depend on the point, right? When you choose a different point, you get a different radius. Okay. So then, let G be the union of all these BRPs over every P and E, right? So every point here is going to have a ball around it, right? Right? Every point has a ball around it. We take the union of all those balls, that gives us an open set. That's what we're going to use as our G, right? Right. Then clearly, G intersect Y is E. Right? Because it definitely contains E, right? And it's definitely contained in E. Right? Because every one of these balls, when you intersect it with Y, is contained in E. So I'm not going to spell that out, but you see that it definitely contains E, and is also contained in E. Okay, so so that's the forward direction. And then going in the backward direction, suppose, right, say E equals G intersect Y, right, for some open G in X, right? So here's our E, and it actually turns out to be the intersection of some G with Y, okay? And we want to show that E is open relative to Y, right? Well, anybody see why that's, can anybody sort of write down why that's true? Anybody, are you able to write it down? Like, give me the argument? You want to show that E is open relative to Y. In other words, you want to show that every point has a ball around it, that when you intersect it, you get something inside of E. Take a minute and write something down. It could be wrong, it could be garbage. But try and write down how you would explain that. Okay, and be sure to write down what you want to show. Okay, like what do you want to show? Okay, talk to a neighbor for a minute. Kaylin, do you want to talk to somebody, or you can talk to me? Talk to somebody else. What?
Yeah.
Yes, yes.
Well, what? I didn't catch what we were supposed to switch. Probably all talk.
Okay,
Yes, there's.
yeah. I was saying that we want to show that E has all interior points, right? Because that's open. But like if G is open and E is the intersection of an open set, and I just kind of feel like E has to be open, but.
I said like if we choose a point in G intersect Y and take the neighborhood that intersect Y, then that's interior.
Okay, what do you want to show? Of course, you want to show that E is open relative to Y. What does that mean? E is open relative to Y. You want to show that
Every neighborhood in E intersect Y is interior. I didn't phrase that right.
not quite right. Yeah. You don't want to say every neighborhood in E, but rather you want to say every point in E. Every point in E has a neighborhood, right? A neighborhood BRP such that what? Every point in here has some neighborhood such that when you
Intersect it with Y.
yeah, such that when you intersect it with Y, that's contained in
E.
E. That's contained in E. Okay, so that's what we want to show, right? And we know that E is the intersection of G with Y, right? E is the intersection of G with Y. So how do we get the neighborhood? How do we get that neighborhood? BRP. Right? E is the intersection of G with Y, right? So every point in here is an element of G and Y, right?
So would we just choose some x in the intersection?
Well, what do you mean choose some x in the intersection? In the intersection, so.
Oh, in G intersect Y to be our point.
Well, yeah, so pick, remember what we want to show. We want to show that any point in E, which is this thing, has a neighborhood. So pick one of them. Pick some B, pick some E in, pick some P in E, which is G intersect Y. Right? Okay, and we want to show that there's a neighborhood around it such that blah, 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 blah. Right? So how do we get that neighborhood? Well, P is in G, right? And G is open, right? G being open means that we can find that P is interior, right? So P is interior to G, right? Because G is open. Anything in G is an interior point, right? P is interior to G, so we know there exists some ball around it that's contained in G. Right? So we know that there's some ball around it that's contained in G. And then when you intersect that with Y, that gives you, that's, right? Then BRP intersect Y is contained in G intersect Y. Right? BRP is inside of G. BRP intersect Y is contained in G intersect Y. Yes? Yes, right? Which is E. And so we're done. Okay. So, okay. So this is sort of more, it's a little bit like definition chasing. There's no real idea here. It's just showing that this definition, that these are exactly the same things. So some proofs, have a clever idea. This one is just checking that the conditions are equal to each other. Okay. Okay. Yeah. That's sort of the definition of trivial. You often hear mathematicians say, this is trivial. They don't mean it's easy. They mean that there's no clever idea involved. Yeah, it wasn't really clear to me for a long time what trivial meant, because in common language, trivial has a certain meaning. But I think what I just said is the true definition, of trivial. There's a funny story about the analyst Hardy, who was one of the great 20th century, first half of the 20th century mathematicians. If you know who Ramanujan is, Ramanujan. You should look up this person. It's an incredible story. Anyway, Hardy is the one who basically discovered Ramanujan. So Ramanujan, I shouldn't get too much into the story, but roughly speaking, Ramanujan was basically a clerk in India who recreated like 150 years of mathematics on his own. He had this one math book, and then sort of extrapolated that. It dated to 1850, I think, and then or maybe 1800. Anyway, he basically recreated decades of mathematical work on his own, and then tried to get his work noticed by writing to mathematicians in England. And many mathematicians were unable to understand what he was talking about, and so they just dismissed his letters as just some crank, just somebody who's just writing nonsense. But Hardy was, a great enough mathematician to realize that Ramanujan was a great mathematician. And so he invited Ramanujan, who had very little education, but he invited Ramanujan to England to work with him, and they produced some great results. So that's sort of the romanticized version of the story. I think they made a movie out of this at one point. Yeah, okay, that sort of takes away my time for the trivial story. But anyway, I'll tell you the trivial story later. No, I should probably tell it right now. Sorry. Okay, so the trivial story is that this Hardy is giving a lecture to an auditorium of people of students, and at one point he gets to a point in the proof and he says, "It is trivial that blah 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 blah," and he goes on. And somebody says, "Professor Hardy, is it really trivial?" And Hardy stops, and he walks around the classroom. He walks around the classroom again, and he leaves the classroom. Sometime later, he comes back in and he says, yes, it was trivial, and he keeps on going. So just to say that, I think this kind of goes along with my idea that what trivial means doesn't mean easy, but just that it doesn't have a brilliant idea in it. Yeah. Okay. Anyway, okay. So right. Okay. So now we've got relative openness. We've got this idea of relative openness. What does it mean to be open relative to right? You've got some set. You've got some metric space sitting inside of another metric space, and you've got a set sitting inside of the smaller one. And the set might be open relative to this one, but not open relative to this one. But what we're going to show now is that compactness is different. That if you're compact with respect to y, you're compact with respect to x. And if you're compact with respect to x, you're compact with respect to y. So there is no relative compactness. Okay, so there's no relative compactness. That's sort of the unofficial name of this. Okay. Compactness is independent of the embedded space. Okay. So suppose we have a compact set. People usually use K for compact sets. Some compact set contained in Y, contained in X. Then the claim is that K is compact relative to Y if and only if it's compact relative to X. So we don't need to say compact relative to something. We never need to say, after this, we'll never say this again, right? Because you just say compact. Okay. So this is another proof that isn't particularly deep. So let's show at least one direction, right? So suppose K is compact relative to Y, and we want to show that K is compact relative to X. In other words, given an open cover, G alpha, where the G alphas are all contained in X and they're all open, right? Given a bunch of G alphas, given any open cover G alpha of K, we want to show that there exists a finite subcover. G alpha 1, through G alpha n of K. Right? So given any open cover, there exists a finite subcover. Okay, so right, here's the picture, right? So we have, here is y, right? And you have some k here. You have some k, and it's compact relative to y. Okay, k is sitting inside of y, and it's compact relative to y. We want to show that it's compact relative to x. Okay, so what you do is you say, well, right. So we want to show that given any open cover of it, right? Given any open cover of it, there must be a finite subcover of it in X. Okay. So we have an open cover of it in X, and what we do is we're just going to drop down and create an open cover of it in Y, right? And then, so remember, we're trying to get to a finite subcover. So what we do is we say, well, look, we can intersect down to an open cover in Y. It's compact in Y, so there exists a finite subcover in Y, and then expand it back up to get the finite subcover, to get the original finite subcover. Okay, so that's the idea. So you say, well, we want to show that given any open cover, there exists a finite subcover. Well, if we take the G alpha intersect Y, if we intersect each of those guys with Y, this is an open cover of K in Y. I should say in X. Right. So we take our open cover in X, we intersect it down, that gives us an open cover in Y, right? Because what we said was that open sets intersect down to open sets. Well, this is open relative to Y. Right? Right, so this is an open cover of K in Y, right? Since K is compact relative to Y, we know that K is included. K is covered by some, so there exists some G alpha 1 intersect Y. We know that there exists some finite subcover that still covers K. Right, by compactness. Is that everybody all right with that? Please feel free to say that you don't know what's going on. Okay, okay, so these guys still cover K, right? But then, of course, G alpha 1 through G alpha and also still covers K, right? Because if these guys cover K, then certainly when we remove the intersections, it's still going to cover K. And so they form a finite subcover of K in X, right? We started off with the G alpha in X, right? We started off with the G alpha in X, and we wanted to show that there's a finite subcollection that still covers K. We drop it down to Y. Compactness gives us that there is a finite subcollection of these things that still covers K. But then we go back up to the corresponding sets. Well, those guys are still going to cover K, and so we've found a finite subcollection that covers K. We've shown that any open cover is going to have a finite subcover. Okay. So Yeah. Okay. I think I don't want to go the opposite direction because it's very similar. Okay. So I'm not gonna go over that. Okay. But everybody feeling okay? 3 or above? Okay. So let's. Most of this chapter is about compactness. The most important stuff in this chapter is, I think, this is sort of like the climactic material of this chapter. Compactness, heading towards this thing called the Heine-Borel theorem, where we say that that in Euclidean spaces, compactness has a very simple characterization. Okay. Anyways, let's go on with more properties of compactness. So the next one is that any compact. So we don't need to talk about relative compactness anymore. We'll just say compact. So this theorem is that if you're compact, then you're closed. Okay. So any compact set is going to be a closed set. Okay. So the proof goes like this. Actually, let me give sort of like a toy version. Okay. And this sort of illustrates a strategy that you want to use when you're proving facts about compact sets, which is try to show it for finite sets first. Okay. But do it in a way that can extend. Okay. So we're going to show finite implies closed. Okay. So finite implies closed. You could sort of do it in a trivial way and say, well, finite means you don't have any limit points, so you're automatically closed, right? So that would be a way, but that's not a way that will extend to infinite sets, right? So you can't when you're executing this strategy, you don't want to go for a proof that won't extend to infinite sets. Okay. So here's how we're going to do it. We're going to show that the complement is open. Okay, so we'll show that here's my finite set. We're going to show that the complement is open, and we're going to do it in this funny way. We're going to say, well, pick somebody in the complement. Okay, so here's my set F, and here's somebody in F complement. Okay. We want to show that F complement is open, and the way we're going to do it is we're going to take distances. So we're going to say, actually, let me just reduce this down to 3 points. Okay. We're going to take distances, right? We want to find an open ball around this guy that doesn't intersect these guys, okay? And so what we do is we take the distance between them and we cut it in half, okay? And we take a ball around it, and we take another ball around it, open balls, so you know that this open ball doesn't intersect this open ball, right? Or we could, if you want, we could make it like 1/3, but half will do because it's open, so there's no point of intersection here, okay? And then you do the same thing with all the other points. Okay. So here I take this guy, right? Here I take half of the distance. Okay, so you know that, each of these balls doesn't intersect its corresponding ball, right? When you take the smallest ball, you know that smallest ball intersects none of these balls, right? Because it's smaller than the guy who didn't intersect with it's smaller than this guy, which didn't it's smaller than this guy, which did not intersect with this guy. Right? So you take the smallest radius, and that gives you a ball that intersects none of the open sets around here, none of the neighborhoods around here, right? And so that tells you that FC is open, right? That this point is interior to F complement. Okay. In other words, F complement is open, and so F must be closed. Okay. And you see why this would fail. This can run into trouble if you have infinitely many points. If you have infinitely many points, well then you might go down to a 0 radius, right? That could be trouble. But compactness allows you to circumvent that. So here's the idea. So that's the idea. Let's now do the proof. So want to show that K compact implies K closed, which is equivalent to saying that K complement is open. Okay. So pick a point P in pick a point X in K complement. We'll want to show that X is interior, right? X is in K complement, the interior of that. Okay, that X is interior, right? Just as we did over here. So what you do is you say for each point in K, we know that there exists, the neighborhood of consisting of the distance from P to X over 2 around P intersect the neighborhood of that half radius around X is empty, right? So take the neighborhood that's half the distance between those 2 points, right? Take one ball around P and one ball around X, the intersection is 0, is nothing, right? Okay. Okay, so now cover P with such neighborhoods, right? Cover P with such cover K with such neighborhoods, right? So for every point in K, right? Here's P. We know that if we take the half neighborhood here, or a half distance, then these guys don't intersect, right? Do that for every single point in K. Okay, we've covered K with such neighborhoods. We've got infinitely many neighborhoods. We're in trouble, but K is compact, so we know that we can throw out all but finitely many of them and still cover K, right? So since K is compact, right? This is an open cover of K. Open cover of a compact set always has a finite subcover, right? Since K is compact, there exist points P1 through Pn such that K is covered by the union of the Pi to X over 2 Pi, and I equals 1 to n. Okay. So we covered it with infinitely many of these guys, but in fact, there's just a finite number where the union of these half distance guys still covers all of K, right? So imagine there's only three neighborhoods. Now we're back in the finite case, right? Just take the intersection, right? Then and then the intersection of the neighborhoods around X, right? So each of these guys has a corresponding neighborhood around X, right? Each of these guys has a corresponding neighborhood around X. Just intersect them, right? And you'll get the smallest one, right? That thing is an open neighborhood of X that does not intersect K, right? In other words, it's in K complement, right? So we've found a neighborhood of X that's in K complement. In other words, X is interior to K complement is open, K is closed. Okay, so that's the end. Okay, that's it for today. See you guys next time.